Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to talk on module Introduction of Glasses, and this is under the paper Ceramic. So after the completion of this module, you all should be able to learn about the glass transition temperature, radial distribution function, and finally cooling rate versus glass formation. So before moving further, let's discuss the basic idea behind it. If we take a metal such as copper, melt it and then cool in the normal manner, then it solidifies in a crystalline structure. In the solid copper, the atoms are arranged in a regular ordered fashion in an FCC structure. In the liquid, the atoms have some short range order but no long range order. The time taken for the solid liquid transition in this case is sufficient for the atoms in the liquid to rearrange themselves in an ordered fashion, characteristics of the crystal. So, in the case of glass, however, although a rigid solid does form on cooling from the liquid state, but its structure is not crystalline. The viscosity of liquid increases as the temperature is decreased and becomes comparable to that of solids. For this reason, a glass is also called supercooled liquid. It has what is called an amorphous structure with no long range order, and in this case the structural units do not get sufficient time to form a crystalline structure before the viscosity increases to a very high temperature levels where the mobility of the structural units becomes very low. Glass transition temperature. Now let's discuss, is liquid to glass formation a phase transition? So for that, let's consider the change in specific volume as a function of temperature as a material is cooled from the molten state. So in this figure, you can see that on a y-axis there is a specific volume and in x-axis it is temperature. So here Tg is the glass transition temperature and Tm is the melting point. So the specific volume V decreases as the temperature decreases, which can be seen from this figure. As we have discussed in the previous slide that the specific volume V decreases as the temperature decreases, so at the melting point there is a sharp drop in V, that is specific volume, as the liquid solidifies into a crystal. On the other hand, if the conditions are suitable for glass formation rather than crystallization, then there is no abrupt change in volume and the liquid continues to cool with nearly same slope. In this state, the liquid is called the supercooled liquid, and this is followed by a range of temperature in which the slope changes to nearly that for the crystal and the material becomes a rigid solid or a glass. So the glass transition temperature, that is Tg, is defined as the temperature of intersection of the slopes in the supercooled state and in the glassy state, which can be seen in the figure on the left hand side. Glass transition is not a thermodynamic phase transition, and let's see how is it. So from the first figure on the left hand side, you can see the variation of specific volume with respect to temperature, which we have seen earlier, and it is written that the specific volume V is given as rate of change of G with respect to P at constant temperature. This specific volume is unchanged at the temperature of the transition, and there is a sudden change in the slope, that is the coefficient of thermal expansion. So, on the below left corner in the figure, you can see the variation of thermal expansivity with respect to temperature. So, from this figure, it is clear that there is a sudden change in the slope, that is coefficient of thermal expansion. The coefficient of thermal expansion is given as 1 by V times delta V by delta T at constant pressure, which is also given as 1 by V delta square G by delta P into delta T. Similarly, the enthalpy can also be signifying the same thing. So on the right side, you can see the variation of enthalpy with respect to temperature. The enthalpy, which depends on the first derivative of G, is given as H is equal to G minus T into delta G by delta T at constant pressure. The enthalpy does not change, but the heat capacity does, which involves the second derivative of the free energy changes at the transition temperature. So, on the lower right corner, you can see the variation of specific heat with respect to temperature, and the expression is given as Cp is equal to delta H by delta T at constant pressure, and this in turn is also equal to minus T delta square G by delta T square at constant pressure. So these changes are compared for the glass formation and crystallization as seen in this figure. The phase transitions in which the first derivative at the transition is continuous while the second derivative changes suddenly are called the second order transitions. Although the glass transition seems to fit this definition of a second order transition, so it is not actually a phase transition. Glass is not the stable but has minimum free energy state of the material. It is in a kinetically locked state, and its entropy, density, etc. depends on its thermal history. So despite all the conditions being satisfied, the glass transition is not a phase transition at all. The radial distribution function. This figure shows the radial distribution function for crystal, gas, liquid, and glass. It can be seen from the figure that the radial distribution function is different for all the four cases. Now students, let's discuss about these one by one. Now let's discuss the radial distribution function of all the four cases one by one in this slide. The structure of matter in any state can be probed by X-ray diffraction and conveniently described by a function called radial distribution function RDF, which gives the density of atoms as a function of distance from any point. It is defined as the atom density in a spherical shell of radius r from the center of any chosen atom. The RDF of a crystal or a gas, liquid, and a glass are compared in this figure. In case of crystal, one gets a sharp radial distribution function, whereas for a liquid and a glass, the behavior are smeared and somewhat similar, indicating no long range order, but a short-range order only, which extend from any atom to one or two nearest atoms. So in the case of materials which form a glass on cooling at the normal rates from a liquid state, the structural unit is usually composed of a group of atoms. Theories of glass formation. So in this slide, we'll discuss about the cooling rate versus glass formation. So when we talk about glass formation, whether an element or a compound will form glass under normal cooling conditions cannot be said a priori. Besides silicates and similar inorganic compounds, most polymers readily form a glass. Many metals can be made to solidify as glasses known as metallic glasses using very high cooling rates of the order of 10 to power 6 degrees Celsius per second. Most metals and compounds can be made glassy in thin film form. A few elements of the periodic table readily form glasses. These are phosphorus, sulfur, and selenium. Here, by glass forming ability, we mean the ability to form glass on cooling at ordinary cooling rates from the molten state. Now the question arises why some materials form glasses and other do not has intrigued the scientists for many years. Before the ideas of the kinetic theory of glass formation were born, the ability to form glass by oxides, which were the earliest known glass formers, are described in terms of structural theories. These theories are important in themselves as they have formed the basis for understanding the glass structure. Later, it became clear that any substance can form a glass provided it is cooled at a fast enough rate to avoid crystallization. As the crystallization involves bringing the structural units in a definite ordered formation with respect to one another, the crystallization would depend on the mobility of the structural units. The mobility in turn would depend on the structure of an individual structure unit. So if this unit is an atom, the mobility is high and the crystallization can occur easily. So in this case, a very high cooling rate would be required to form the glass. However, if the structural unit consists of group of atoms, then their mobility would be low and a glass can form at lower cooling rates, even at the normal cooling rates. So it is usual to discuss the structural theories of glass formation, but in this module, we will be discussing the kinetic theory first and then moving further. So first we will be discussing about nucleation. Let us consider the process of nucleation. In it, a number of structural units in the liquid come together by diffusing through the liquid to form a crystalline structure. This structure is called embryo. These structural units can be single atom, as in the case of a metal, or they can be a formula units such as SiO4 in case of silica. As the basic formula units in the liquid come together to form crystalline embryo, an interface is created between the embryo and the surrounding liquid. This interface has a certain surface energy. So in the beginning, when the embryo is small, the increase in surface energy, due to this, the liquid changes into crystal and there is a transformation because the surface to volume ratio of an embryo is larger due to its very small size. The embryo formation therefore causes an increase in energy, and the embryo tends to dissolve back. At any time, there would be a distribution of sizes of the embryo in the liquid. As the embryo size increases, the decrease in the volume free energy approaches the increase in the surface energy until at some size, the two are equal in magnitude. This size of the embryo is the critical size because further addition of a single formula unit results in a net decrease in the free energy and the embryo is now stable. Embryo has now become a nucleus and this size is called critical nucleus size. This critical nucleus size can be derived as follows. So, if the thermodynamic barrier for the formation of a nucleus is delta G and the kinetic barrier is delta GD, then the rate of nucleation can be expressed as I is equal to 8 times exponential minus delta G plus delta JD by KT, where A is a pre-exponential factor which can be approximated as A is equal to NV times KT by H, where NV is the number of formula units of the crystallizing component phase per unit volume of the melt and H is the Planck's constant. An expression for delta G is now can be derived. So for this, let the change in the free energy per unit volume between the liquid and crystal be delta GV. Note that delta GV is a negative quantity because crystal is more stable phase. Let sigma be the surface energy per unit area of the liquid-solid interface. For the formation of a spherical embryo of radius r, the change in volume free energy is delta GV times 4 by 3 pi r cube. The change in surface energy is 4 pi r square times sigma and the total change in energy, that is delta G, is given as delta GV times 4 by 3 pi r cube plus 4 pi r square times sigma. The variation of the two terms on the right hand side and of the total energy with radius is shown in this figure. So from this figure, it is clear that as R increases, the surface energy term dominates at small r and the total free energy increases at first, and after a critical value of R, the volume free energy term prevails and the total free energy decreases as the R is further increased. The critical value of R, that is R dash, is at the maximum in the free energy curve and is obtained by the equations or by the derivation of delta G to 0. So the equation becomes del of delta G by del R is equal to 4 pi r square times delta GV plus 8 pi r sigma. At r is equal to r dash, delta at r is equal to r dash, del of delta G by del R is equal to 0 or r is equal to r dash, which in turns equal to minus 2 sigma divided by delta GV. So the embryos smaller than r dash are unstable and the free energy barrier associated with the formation of critical size nucleus is obtained by putting r is equal to r dash. So delta G dash is equal to 16 pi sigma cube divided by 3 delta GV square. As an example, in case of silica glass, the structural units can be taken to be SiO4. In the liquid state, these units further link together to form larger units. In case of the polymers, most of which also form a glass on cooling, the structural unit may be segments of a chain and each segment containing a few carbon atoms. These large structural units lead to a higher viscosity of the melt. The units have a low mobility and are not able in the limited time available during the normal cooling. So, it takes time to arrange themselves in a crystalline structure. On lowering the temperature, the viscosity increases rapidly and the material becomes a rigid solid with amorphous structure. So students, let's now summarize what we have learned in this module. We have understood that some materials solidify in an amorphous structure when cooled from the liquid state. The viscosity of the liquid increases as the temperature is decreased and reach the values of the characteristics of the solids. In case of such materials, the structural units are not able to arrange themselves in an ordered fashion and the crystalline structure in the temperature range where the viscosity is still small for the mobility of these structural units to be high enough for this purpose. So, if the specific volume is plotted against the temperature during cooling from the liquid state, there is a change in slope of some temperature. This temperature is defined as the glass transition temperature. It is not a fixed temperature, but it depends on several factors. Thus, the glass transition temperature increases if the rate of cooling is increased further. The radial distribution function gives the density of atoms as a function of distance from any point. So, it is defined as the atom density in a spherical shell of radius r from the center of any chosen atom, which we have already discussed in this module. Its shape is nearly same for a glass and for a liquid. In contrast, the radiant distribution function of a crystal has sharp lines indicating the atoms are located in shells of discrete radii around any atom. Although during the glass transition, many thermodynamic quantities behave in a manner similar to a second order phase transition, which we have seen in this module, but the glass transition is not a second order phase transition. Rather, it is a kinetic phenomena. It is not possible to say priori whether a given substance would form a glass or not. Many ideas based on the structure have been proposed to predict the ease of glass formation. However, in fact, many materials can form a glass if cooled at a rate faster than critical cooling rate. Thank you.